We are now continuing with Module 12 of this Math 137 online class. This is part 3. I'm going to go ahead and sort of let all of you peek behind the curtain of these videos in this class. The last video, we were working with complex numbers. And we talked about there were 2 ways to express complex numbers and 2 ways to sort of graph them. We discussed the rectangular form where you have x plus yi. And then we said you can also have the polar form where instead of x and y, like your typical graph, we can use polar coordinates and we can express a complex number as r times cosine theta plus I sine theta. And that's where the last video stopped. And just so you know, that last video was actually made a couple of years ago. And this video, we're having to do a little updating because when that last video was made, they updated the textbook that we're using for this class. Normally, when they update a textbook, the changes are pretty minor and you don't really notice it. That's why all the videos for this class didn't have to be modified or changed because the material really was the same. But this is the one part of the textbook where they did make a pretty drastic change, and therefore some of the homework problems changed. And now we have to come in and sort of teach some of the new stuff they put in. So I say that to say that this is the point right here in the last video where we stopped. And if you go back, if you remember the last video, we did some problems. And when we expressed the complex number in polar coordinates, if you look back, you'll see that the angles are in degrees, which is fine. But from now on, and in the homework and in the quiz and on the test, we're going to now start doing problems where instead of using the angle in degrees, we really want, and we're going to start always using the angles in radians. So from now on, we need to use or express angles and radians, and you'll see why in a minute, why that becomes important. So here's the new thing that has been added to the textbook, and it makes sense because it can be a pretty useful principle that we're going to use. There was it's a very, very famous mathematician. His name was Euler. Matter of fact, what he came up with, which has been used a lot, is called Euler's formula. And it relates to this polar form of a complex number. Because as it turns out, Euler discovered somehow, I don't know, these people are brilliant, that cosine of theta plus I sine of theta, that whole thing can be rewritten as e to the I theta. E, remember, is the natural exponential function. That's that special number. We call it E. So in some crazy way, you know, the way God made the world, that we're talking about cosines and sine and complex number. And this thing here actually ends up being the same as the exponential function of I theta. Now for this, little formula here, you have to plug in the angle and radians. It's almost like, you remember way back at the beginning of class where we had the arc length. Remember we had S equals R theta, and the area of a sector 1/2 R squared theta. And for these formulas to work correctly, you had to plug in the angle in radians. If you plugged it in degrees, it would be incorrect. Well, that's how this is. So the idea is, the first thing is Euler's formula says that this cosine plus I sine of theta equals E di theta. Therefore, now we have actually a third way to express a complex number. So they replaced all the cosine and sine stuff with this exponential. And this, I'll write it down here. So here's the rectangular form, X and Y. Here's the polar form. The key is R and theta. Turns out we call this the exponential form. Now it's similar to the polar form, because the polar form, the keys are, you need to know R and theta to write the complex number in polar form. Well, if you want to write the complex number in the exponential form, you also need R and theta. So going back and forth between polar and exponential form is very simple. It's just, you have the same information, you just rewrite it and express it differently. But now we have three forms of complex numbers. In the previous textbook, they mainly just stopped after the polar form, but now we're going to include the exponential form. And there you will have problems, homework problems, quiz and test problems, where they will also ask you to express the complex number in the exponential form. So what I'm going to do now, just as sort of to review this new aspect since the last video, let's go ahead and do one more problem. We're going to take a complex number written in the rectangular form, and then we're going to express the complex number in both polar form and in the exponential form. And it's actually going to be the same thing that we've just done, except the big difference is, okay, so I didn't make this clear. For now on, when we express a vector in polar form, we're going to go ahead and also put the angle in the polar form in radians. It's almost like, since in this exponential form, this angle has to be in radians, just to keep it simple, to not be confused, to not be going back and forth. The textbook decided whenever you express a complex number in polar form, they don't want the answer anymore to have the angle in degrees. They're going to want it in radians. So for instance, if you had some problem before where maybe the angle was 45 degrees and you put 45 degrees here and 45 degrees here, they don't want that anymore. Instead, they would want you to put cosine of pi over 4 and sine of pi over 4. And that's because now we're using this exponential form, and because this angle always has to be radians, it makes sense to be consistent. So for now on, when we express theta, it's going to be in radians. So let's do one problem where we show you how that works. So let's start with, here's a complex number, square root of 3 minus I. So basically, this is in rectangular form. So X is the square root of 3 and I is the Y. So we want to go ahead and rewrite this complex number and put it in polar form. And then after we put it in polar form, we will go and also write it in exponential form. So you can now see the three different forms. So we've already gone over this, so we'll try and work through it quickly. To determine R, right? R is you take the sort of the X of the rectangular form, We're going to square it. And we take the y, which is -1, and we square it. And then, of course, we have to take the square root of the sum of these. So square root of 3 squared is 3, -1 squared is 1. So it's 3 plus 1, 4. All right, so now we know that r is 2. So now let's go find our angle. The angle is always a little bit trickier. So once again, the angle is based off the sort of formula. The angle equals the inverse tangent of y over x. In this case, the y is like -1. The x is square root of 3. Now, what I typically do in cases like this, I sometimes just, I know this is an inverse tangent, but just to sort of, and what I always encourage you to do, which even I forgot to do a really, really quick rough sketch of this complex. So here's the real coordinate and the imaginary, sort of the x and the y. Let's just see where this is, because this becomes important when we want to find our angle. So square root of 3, I think, is like 1.4. It's not really important. It's just a positive number. Actually 1.7. So if we were to graph this, it's like the x is like 1.7 and the y is -1. So we're probably maybe down here. So the key is we're in like the 4th quadrant. So this needs to be our angle, right? Because when we do the math here, we know that what this calculation will give us is probably this angle right here. So we'll have to do a little bit of math to get the angle we need. So when I do this kind of problem, just to sort of get my head straight, sometimes I rewrite this because it helps me to sort of see what's going on. And instead of writing the inverse tangent, I sort of flip it around and I say the inverse tangent of -1 over square root of 3 means the same thing as basically the tangent of what angle equals -1 over square root of 3. And for me, this is actually a special angle. So I'm going to think of this as, let me go find an angle where the sine over the cosine equals 1 over square root of 3, and more important, or as important, it's also negative. So I know here in the 4th quadrant, that's where sine is negative, cosine is positive. So I'm looking for an angle, one of the special angles in the 4th quadrant, that would give me this. And hopefully you see that if I look at 11 pi over 6, 11 pi over 6, the sine is negative 1/2, and that 11 pi over 6, the cosine is square root of 3 over 2. And when you simplify this, it's -1 over square root of 3. So for that confirms that actually I didn't need to worry about, if I had done some kind of calculation with my calculator, it would have given me this angle. But because I sort of common sense this out, I was pretty much able to come up with right away that the angle is 11 pi over 6. So bottom line is r is 2, theta is 11 pi over 6. So to write this in the polar form, I've got what I need. This complex number is, you take your r, cosine 11 pi over 6 plus I times the sine of 11 pi over 6. So the big difference is, in the previous video, we would have expressed these angles in degrees, but now we want them to be in radians. And once you have your polar equation, the exponential equation is very simple, right? So just to review, here's the polar equation. The exponential, the r, start with the r again, and then you have e to the I theta. So I'll just, since this is new, I'll write it again down here just to make clear what we're doing. So r is 2. Now here's something, it doesn't really matter. You know, whenever through the years, whenever you're at complex numbers, you sort of get used to putting the I last. In the book and in this equation, like the I comes first, but you're going to see when I do some examples, I'm just so used to putting the I last. I just like to do that. And it doesn't matter. So I'm going to just do that. So theta is 11 to the power over 6. And then I put times I, because I'm just used to always putting the I last. So just to summarize, here's this initial complex number in rectangular form. We wanted to rewrite it in polar form, which we've already learned about. So this was sort of review. So here's the polar form. We found r to be 2, theta to be 11 to the power over 6. Polar form, but now we've got this new way to look at it where we also can write it in what's called exponential form. 2e to the 11 to the power over 6 times I. Now here's where, having been able to express a complex number in exponential form, there's a pretty big payoff. And that is because there are going to be times where in math, you may want to multiply or divide, or even, well, let me just show you. So in a few minutes, we're going to take a complex number z1, and then we're going to have a second complex number z2, and we want to multiply the complex numbers, and we want to know what does it equal. And then we're going to turn around and maybe we want to divide the complex numbers and see what it equals. And then we may want to take that first complex number and maybe raise it to the 4th power. So these are the kinds of things you want to be able to do with complex numbers. In this case, for these first couple, 2 complex numbers. Now, if you think about it, if you were to try and do these kinds of math operations in either rectangular form or polar form, it can get pretty messy, especially if you can imagine trying to take a complex number, raise it to the 4th power, like you have 4 parentheses to multiply out. That would be horrible. And if you had a complex number in like a polar form and you're trying to divide these, very messy, hard to simplify. However, now these operations here become actually pretty easy, very straightforward if you do them if anytime you have like 2 complex numbers, you want to multiply or divide, or if you want to take a complex number and raise it to a exponent, if the complex number is in the exponential form, it becomes a very, I guess I'll say it, easy and straightforward problem. If these complex numbers are in polar form or rectangular, it's a lot messier. but if they're in exponential form. So a lot of times what we're going to do, and we'll do some examples in a minute, if we're given two vectors and the vectors are originally in rectangular form or even polar form, the first thing we're going to do is we're going to convert the vectors into the exponential form. Because once we put them in the exponential form, then these operations become very straightforward. So let's just, as a way sort of to see it sort of theoretically, almost like in a formula, I will show it to you and then we'll do some examples. So let's just say that let's just assume now that we have the two vectors and we're going to express them in the exponential form. So we'll call vector z1, therefore we'll call it r1 e to the theta 1I. Then the second vector will look the same, except the subscript will be 2. So two vectors written in the exponential form. So let's first see what happens if we multiply these. So z1 times z2. So z1 is the r1 e to the theta 1I times z2, the second complex number, r2 e to the theta 2I. Now, let's go ahead. R1 and R2 are sort of like numbers or coefficients. Let's just move them out front. R1 times R2. Now, if you remember, with your exponent rules, multiply two exponents with the same base. What you do with the exponents, the product rule says you add them. So hopefully you can see, let me go over here to the side. So I'm eventually going to add those exponents. So it's going to be this. But you know what? If I factor out the I, so it's going to write that here. So we're going to have e to the I theta 1 plus theta 2. So the nice thing, maybe I could even say the beauty of this is, if I have two complex numbers and they're written in the exponential form and I'm going to multiply them, what do? I simply multiply the r's, r1 times r2. I write e to the I, and then I take the angles, the thetas, and I simply add them, and that's my exponent. And I've multiplied it. And if I want to, so what can happen sometimes is you're given your initial two complex numbers in like rectangular, say you're given to rectangular form. What you would do is you would take those two complex numbers, you would convert them to the polar form and then to the exponential form. So they end up, your two complex numbers would look like this. So now when you multiply them, it's a very easy process and you have your answer here. And then you would take this and then you would convert it back into the polar form. And then actually you wouldn't even need to do the polar form. You could just take this and convert this back into the rectangular form. If that doesn't make sense, in a minute, we'll do an example and hopefully it'll be clear. But let's also go ahead and see what happens if we would happen to have two complex numbers which we want to divide. So once again, if I just write this out here, it's going to be pretty clear what happens. So in this case, the R1 now and R2, it's R1 divided by R2. Once again, exponent rules, quotient rule, and if you simplify, hopefully it's pretty clear to you that you end up with this. So when you multiply, ends up you add the two angles. If you happen to divide, you subtract the two angles. So once again, if you ever want to divide two complex numbers, if you get the complex numbers in exponential form, it's pretty simple. And actually, let me go ahead, although it's not in my notes. If we do this thing, and actually this little, so now what happens if you raise it to an exponent? And actually this has a name. I assume looks like some French name, de Moivre. This is like his little discovery, de Moivre's formula. So if you want to take a complex number and you want to raise it to a power or to an exponent, I won't show you how they discovered it, but here's a little formula. It's also pretty straightforward. So if it's in exponential form, you take the R and you simply raise it to the exponent. And then I guess I should put R1. Very nice and neat and straightforward. Now it is a formula, so I realize that it's a little messy, but when we do the example, you'll see that this is actually very straightforward. If you've got your complex number in exponential form, you just take the R, and if you're doing like to the third power, then you put a 3 here. You take 3 times your angle, and you've got this complex number raised to a power, which can actually be quite messy, but this formula makes it actually very simple. All right, so let's do an example. So what we will do is, let's go ahead and we will start with a, let me look at my notes. I think I want to do, yeah. Let's do this. Let's start with a rectangular complex number and rectangular form. And then let's, well, as I'm teaching this, I'm sort of changing up how I'm doing it. So, all right, let me stick with my notes so I don't mess things up down the road. So let's say we were given a vector z1, and we're actually, just to save some time, make it simple, we're going to say they gave it to us in polar form. So 3 times the cosine of pi over 9 plus I times the sine pi over 9. Now, hopefully it's clear to you that, so the R is going to be 3 and the angle is pi over 9. So just, yeah, that's going to be like in the first quadrant, but don't think it's really important right now. I'm going to go ahead, because it's so straightforward and simple. Here is the equation in polar form. Let's write an exponential form, right? So exponential form, you just write the R first, then you have E, and then you take your angle times I. So polar form, exponential form. Here's my second complex number. And we're going to say it's 5 times the cosine of 5 pi over 9 plus I sine 5 pi over 9. Now, if I want to write this in the exponential form, R is 5, E, my theta is 5 pi over 9 times I. So now let's multiply these. So if you can imagine, if I sort of covered this up and said, let's multiply these two, I mean, it'd be sort of messy and I don't know, don't really want to think about it. But because now we sort of have this, in fact, I'll put it up here. So when you multiply, just to refresh your memory, actually, I'll write it here just so it's clear, rewrite it since you're doing it the first time. The formula says R1 times R2 e to the I, and then you add the angles. R1 is 3, R2 is 5, e to the I, theta 1 is pi over 9, plus theta 2, which is 5 pi over 9. There, we've now multiplied those two complex numbers. Now let's go ahead and simplify it. So this would be 15 pi over 9 plus 5 pi over 9 is 6 pi over 9, which is actually 2 pi over 3. So there is those two complex numbers multiplied in the exponential form. And since they gave us this original problem in the polar form, a lot of times they will want the answer in the polar form. But once again, it's pretty easy because it's just 15 cosine of theta 2 pi over 3 plus I times the sine of theta. And then sometimes, just for fun, they will actually also ask you to give the answer as a rectangular number. We can do that here, especially because these are special angles, right? Cosine of 2 pi over 3, 2 pi over 3 is over there in the second quadrant. The cosine is going to be -1/2. So -1/2 times 15 is -15 over 2. The sine of 2 pi over 3 is square root of 3 over 2. So it's going to be like 15 square root of 3 over 2i. So there would be the answer if they wanted it in a rectangular form. Now let's go ahead and divide these. So once again, I will write the formula down here since it's fairly new. So it ends up being R1 over R2 e to the I theta 1 minus theta 2. So for our problem, once again, we can't fit it on here all, but R1 is 3, R2 is 5. E to the I, and then we're going to have pi over 9 minus 4 pi over 9. So I'm just looking at my notes. I don't want to make any math errors. Whoops. See, I did make a mistake here. So it's supposed to be 5 pi. Yeah. I wrote 4 pi. I was looking at the answer. Sorry, this actually should be. All right, I'm glad I caught that. So theta 1 is pi over 9, theta 2 is 5 pi over 9. So theta 1 minus theta 2. So when we simplify this a little bit, we have 3 over 5 e to the I, and then it's pi over 9 minus 5 pi, which is negative 4 pi over 9. Now, one of the sort of rules of the exponential form, they don't want you to have a negative angle up here. So we don't want to leave this as negative 4 pi over 9. So if we go over here to the side and think about it, let's figure out, we want this to be a positive angle. Negative 4 pi over 9 is maybe probably almost, it's probably around here maybe. But what we really want to do is express, this would be the positive angle. So what we can do really is, if we take 2 pi minus 4 pi over 9, we would have this here. So what we really want is 2 pi minus 4 pi over 9. Well, 2 pi is going to be 18 pi over 9 if I get a common denominator. So really, this is going to be 14 pi over 9. So how they really want us to express this as a positive angle. E to the I times 14 pi over 9. And then I won't do it because it's just basically copying things down. You could take this and rewrite it in polar form if you wanted to. So the idea is now, if you have two complex numbers and you want to multiply or divide them, if you put them into the exponential form, it's a pretty straightforward process. Now, the last thing we want to do is to take a complex number and raise it to a power. And just for fun, let's start, instead of working with this, let's start a new problem. Matter of fact, maybe we'll take a new page. Here, we're going to start all the way back where we're going to take a complex number that's in rectangular form. Looks pretty straightforward. Z equals 1 plus I. But what we want to do now is determine what is Z to the 5th, which basically means what is 1 plus I to the 5th. Now you could do that sort of algebraically, but it would be a little painful and messy and could take a while. But instead, let's be smart and let's use our polar coordinates in the exponential form. So here's what I want to do. I just want to take 1 plus I, and I want to eventually, I want to take this complex number and I want to express it in the exponential form with polar coordinates r and theta. First thing we'll do, well, we know how to get r and theta. We've done that many times before. R is going to be 1 squared plus 1 squared, right? This is like the x and the y is the coefficient in front of the I. So r is like square root of 2. And then theta, inverse tangent of 1 over 1. Now we know that this complex number is in the first quadrant. So this is pretty straightforward. If we were to graph this, it's pretty obvious that it's 45 degrees, but now we want to make sure all of our angles are in radians. So that angle is pi over 4. So I'll write it again, R E in polar form, 1 plus this 1 plus I complex number. I can express as square root of 2 times E to the power over 4 times I. So I've taken this complex number in rectangular form and rewritten it in exponential form. And now I go back and look at my formula that Demoivre came up with. I'll write it again here now. A complex number raised to the power n is simply r to the nth power e to the n theta times I. So for us, z to the 5th, r is square root of 2, square root of 2 raised to the 5th power times e to the n theta. N is 5, theta is pi over 4, 5 times pi over 4 times I. If we simplify this, square root of 2 to the 5th power, square root of 2 times itself 5 times. Square root of 2 times square root of 2 is 2. And that happens again 4. You can work it out if you need to on paper, but square root of 2 to the 5th power should be 4 square root of 2. And then 5 times pi over 4 is just 5 pi over 4. So that wasn't too bad. And now, since we started out our initial complex number was in rectangular form, I want to end up with this rectangular form. Let's go ahead, because I think sometimes in the homework or quizzes, sometimes they go and have you write this in polar form. Let's write this in polar form. It's not very hard. You just plug things in. You have r 4 square root of 2 times the cosine. Actually, as I'm doing this, I sort of misspoke. You really need to write this in polar form to determine the rectangular form, because when I write this out, this is the way actually we determine the rectangular form, because we actually do this calculations here. So in exponential form, if I rewrite it in polar form, now to get the rectangular form, I need to sort of multiply out these parentheses and evaluate these trig functions. Cosine of 5 pi over 4, that's down in the 3rd quadrant. That's a negative square root of 2 over 2. So basically I'm going to have 4 square root of 2 times negative square root of 2 over 2. And then for the second part, it's also going to be 4 square root of 2 times negative square root of 2 over 2. Sine of 5 pi over 4 is negative square root of 2 over 2 times I. I want to be sure. Let me look at my notes because I always hate to do problems and then make a mistake. And it confuses everybody. So I want to confirm that I'm doing this correctly. Yep. So now, if I simplify this, hopefully notice square root of 2 times square root of 2 is just 2. So these 2 and this one cancel out. And I'm left with negative 4. Same thing happens here. Square root of 2 times square root of 2 is 2. So these are 2, and I got 2 here. Those all cancel. So I'm left with negative 4i. So it's interesting how this was our initial problem. 1 plus I raised to the 5th power. We get down to here. Turns out it's negative 4 minus 4i. So this is why when we have complex numbers, we convert them to polar coordinates. And what's especially helpful is when you write the complex numbers in the exponential form. Because then if you multiply vector or multiply complex numbers or divide complex numbers or raise a complex number to an exponent, it's not very difficult. Now there's one more. Well, let's do this. I thought about taking a break, but let's just keep going instead of having another part, even though this will make it a little bit longer. But let's do one more example. How about if here is a complex number in polar form. So there it is. Turns out they want to cube this complex number. Now, unlike the last problem where I had to convert from rectangular to polar coordinates, I've already got polar coordinates here. So the nice thing is I can look at the complex number in here, and I can just go ahead and rewrite that in the exponential form, which is going to be r, right? R is 2, e power 9 times I. So now I want to cube that. And just to remind you, what's the formula say? You just, in our case, I'm going to cube the r and then multiply the angle by 3. So cube the r, and then the angle is pi over 9 times 3. Wow, not very difficult. If I clean this up, this is 8 So it's like this, 3 times power over 9 would be power over 3, e to the pi over 3 times I. So there's the answer in the exponential form. And if they want the answer in polar form, it's not too hard to do. 8 cosine of pi over 3 plus I times the sine of pi over 3. Matter of fact, I think in the book, when I did this problem, they actually ask you to then also give the answer in rectangular form, which is not too bad since pi over 3 is a special angle. So cosine of pi over 3 is 1/2. Looks like it's 4. Sine of pi over 3 is square root of 3 over 2. So it's 8. Let's do this. 8 times square root of 3 over 2. So it's like 4 square root of 3 times I. Wow, it's amazing how you would think this would be pretty complicated, complex number raised to the third power. And it took me like 4 or 5 lines to do all the forms and everything. So that's pretty nice. Okay, there's actually one more. They have 1 or 2 problems, which can be a little messy, but let's just bite the bullet and go ahead. And you can also use polar coordinates and exponential stuff to find what we call complex roots. Key here is the word root. Just a reminder, what is a root? So we call this a square root of 4, which is 2. We would say the cube root of 27 is 3. So what happens is we sort of call this 3 as like the root. And here there's a 2 there. This is a root. So the complex root is basically you're taking a complex number. You're taking some kind of a complex number. And you're trying to find the roots of it, like maybe the cube root of a complex number. And because it's a complex number and we have angles and stuff, you can choose how many sort of complex roots you want. It can be a little confusing. And here's the formula, which is a little messy. So if we have a complex number in the exponential form. So once again, this is why, oops. Sorry about that. If we have a complex number in the exponential form, and we want to find the third root of it, here's the formula, and then we'll do an example. Formula sometimes can be confusing, but this will be confusing at first, but when I do the examples, it'll sort of make sense. So the n is the root we're looking for. So if we're looking for the cube root, n would be 3. If it's the 4th root, n would be 4. But here's the formula. So the nth root of r, and then this is where it really gets sort of messy. You got the I here. Then you put 1 over n, and then in these parentheses, you put theta, your angle, plus 2k actually, Well, I'll go because the book calls it 2k pi. I could almost call it something different, and it may not be quite as confusing because now we have a k. Let's do this. So trying to explain the formula, let's actually do a problem because that's probably going to be easiest. Let's say we're asked to find the complex cube root of -1 plus square root of 3i. So we're going to start with a complex number in rectangular coordinates. So the complex cube root, if you wanted to sort of visualize, it's basically saying, what's the cube root of this? Although in the world of complex numbers, there's going to be, you'll see there's actually going to be three answers for this. To use this formula, our complex number needs to be in polar form. So we got to first put this in polar form. So we've done this a lot now. Hopefully we can do it fairly quickly. -1 squared plus square root of 3 squared. That's going to be 1 plus 3. Square root of 4 is 2. That's nice. And actually, I think we've done this before. But anyways, if we look for the angle, inverse tangent, square root of 3 over -1. If we look at this original complex number, this is actually going to be in quadrant 2. So this helps us. So I like to think about this once again. I'm looking for an angle where the tangent is square root of negative square root of 3. And I like to think about tangent as sine over cosine. And if I go over and think in quadrant 2, I think of the sine of square root of 3 over 2, and the cosine is -1/2. And what angle is that? That's actually 2 pi over 3. So I did all that to realize my angle is 2 pi over 3. So let's do this. We'll summarize that. So now I've got, here was my rectangular complex number. For polar coordinates, r is 2, theta is 2 pi over 3. So now let's write this complex number in exponential form. I'll just call it z for now. So it's r e to the theta times I. Now, how do we apply this form? It gives us roots. Let me explain this now. So n is the root. So for us, n is going to be 3. But the way this works is you've also got this k. K is always 1 less than n. K is always n minus 1. And what's going to happen is we're going to have to do this 3 times, because what happens is k is like a counter. You first do the formula with k equal to 0. Then you do the formula with k equal to 1. And then you do the formula with k equal to 2. In other words, n is 3. You subtract 1 from n to get k, and k always starts at 0, and you start stepping up k's until you're done. That means I have to do this equation 3 times. So let me write the equation and then we'll do it. So we'll write it here again. C of k equals. Now I realize this is a little confusing, but it's almost like a formula. Once you sort of see it done, you can just follow the formula and it's not that bad. So for us, there's theta. We know n is equal to 3. And now we're going to have to do this equation 3 times. The first time is when k is 0. So we call this z of 0. N is 3. R is 2. And we just plug stuff in. I, 1 over n is 3. Theta is 2 pi over 3 plus 2k pi. K is 0, so 2 times 0 times pi. So we simplify this. Cube root of 2. 2 times 0 times pi. This is 0, so we're left with 2 pi over 3. 2 pi over 3 times 1/3 is 2 pi over 9. So I have e to the 2 pi over 9 times I. This right here is what we call the first root. It's z of 0. But there's actually going to be 3 roots because k can be 0, k can be 1, k can be 2. So we have to keep doing this until we get to k equals 2. So now when the k, so this is when k is 0. This one is now when k is 1. So use the same formula. The only thing that's going to change is the k. Everything else stays the same except this k right here now becomes 1. So cube root of 2 e to the I times 1/3 2 pi over 3 plus 2 times now 1 times pi. So now we need to sort of simplify this. Now this is 2 pi plus 2 pi over 3. Of course, 2 pi, if I want to add it to 2 pi over 3, I think of 2 pi as 6 pi over 3. So 6 pi over 3 plus 2 pi is 8 pi over 3. Multiply it times 1/3 is 8 pi over 9. I'm skipping some steps, but because this video is going so long. E to the I times 8 pi over 9. So this we say is a second root. But now we have to keep going because we have to go up until k is equal to 2. So now we have one more to do. And once again, the only thing that changes is I'm going to stick in 2 for k. So it's 2 pi over 3 plus 2 times 2 times pi. So now we have 4 pi plus 2 pi over 3. 4 pi is 12 pi over 3. That's 14 pi over 3 times 1/3. 14 pi over 9. I times 14 pi over 9. So when they say the cube root of a complex number means there's actually going to be 3 sort of answers. There's the first one. There's the second one. There's the third one. So this is a little messy and crazy. I guess when you have this problem in the homework, you can pretty much follow the formula and you can figure this out. And yeah, I admit it's pretty messy and pretty nasty, but hopefully you can follow this example and get the answers. All right, so that was a lot going on there. So hopefully this will help you with your homework and the quizzes and the exam.